Can I start now?
Yeah. Yes, sir.
Okay. Hello, everybody. Thank you very much. I'm here there. Voice. Because- Hello.
Yes, sir. Yes, sir.
Oh, okay.
You may start,
Okay.
sir.
Okay. Thank you very much for joining and giving me a chance to present our work. This work is done while I was in Colombia. The project was awarded from National Monsoon Mission, and and I would like to thank my colleagues like Abik, who was our graduate student, led this work, and Andy and Azhar and Aaron and Abhijit and Sushmita from IITM. So why seasonal forecasting matters? Because forecasting at every time scale matters. Like a weather has their own stakeholders, decision making required. Seasonal forecast has its own merit and importance, and as well as the subseasonal forecast also help users in the various sectors like in, in agriculture, planning, like water resources management, even in travel or transportation. So, specifically for India, it's important for agriculture and water management and flood and drought preparedness. So, what is the challenge? Because in the weather, uh, the skills comes from initial condition and which is come down very quickly, and and the ocean start playing a role on the at the longer scale, and then time scale between like a days to 1 month, which is called subseasonal time scale. That's both main driver, initial condition, and the mean background state doesn't provide any source to that predictability, and the somewhat predictability comes from land's initialization and maybe some from MJO or MESO at that time scale, though this skill as compared to weathers were very like, drastically low. Low, not drastically low. So, what there is two type of forecast we can do in deterministic way and the probabilistic way. You can see this recent initial forecast from extended range of IITM. It's 17th of June. Then deterministic forecast tell users what may happen in the magnitude, how much rain going to happen at particular grid point, and what will be the anomaly. And you can see that this is the maybe half of till July and the first 4 weeks below normal mostly in India first 3 weeks. And on the right hand side, you can see that this is the same forecast issue in probabilistic format from IRI, and this is issued on 19th of July and valid from Monday to Sunday, that week 20 to 26. And you can see that also. This map show that um, probabilistic forecast issued like a terciles, a three value at particular grid point. When we come to plot, we plot the dominant tercile. So in the central India, north and central India, we can see that below average rainfall is likely. The probability is high, exceeding 60%. Some places even more, and the southern peninsula is likely to have above normal rainfall um, uh, in the first week. In the second week, you can notice that the useful information is only a few grid points, and that is the challenge with specifically the probabilistic forecast and with the current method. So those probability issued by these methods is like very close to each other and less than 40%. So those points doesn't give any actionable probability or confidence to those forecasts. So, how probabilistic forecasts are constructed? There are two ways. First is just you have um, a climatological probabilist curve, PDF, and then you can find those thresholds, 33 and 66, based on your like a use case, if the tercile forecast, and then you can count how much ensemble member fall ensemble members forecast fall in each category, and then you can assign those probabilities. That is called counting method. Another method is you have to construct the PDF for similar to the for climatology. We have a forecast PDF. You compare those to PDF, and area under the curve give you the idea of if the forecast have which category of forecast is going to dominate as compared to climatology. Both have their own merit. If you have ensemble members, a large number of ensemble members, then you can uh, counting is also a good method. But if your ensembles are small, then counting can be noisy. And similar, this probabilistic things when it's required assumption about your probabilistic distribution. So rainfall is very tricky. Daily rainfall has gamma. Seasonal rainfall may be near normal. So assumption can hurt you sometime while you're constructing the PDFs. So why calibration needed? Um, because model have some their biases. Um, Either it's a mean bias, PDFs are shifted in mean, or either it's mean bias and the variance is too small. These both do exist. That is generally most of the in these cases. And third is the PDF variance is too large. That doesn't happen. And in the reality, the models issue the forecast which are variance is small compared to um, observations variability. So various strategies used to create that, replicate that observed variability with the by designing the strategy of initial models. So that is the purpose of calibration. We want to make a forecast. Like if we have a many forecasts as similar to climatology, and if we plot their distribution, they should look identical. And what in this project, our research question was to address this issue that our forecast reliability is good. Currently, IR used EL calibration method, that is a grid by grid logistic regression, extended logistic regression. And in analysis, it has a good reliability, but problem it has a low sharpness and a modest scale. And if those scales are modest, it may come from your dynamical model. Maybe we are not doing uh, calibration well, and we want to work. We cannot do anything with how the forecast come from the dynamical model, but we can certainly improve our own calibration. So that was our motivation in this study. So we have the data from GEFS version 12. It is from 1989 to 2019. That is not that's a reforecast data, not a forecast data. It has ensemble members, and now GEFS start every day, um, 35 day. Once it start like for 35 days, and we use the Wednesday start, and we have high resolution observation data from IMD, but we convert it into one degree, and we focus on in monsoon season, and the lead was accumulated forecast for week 1, week 2, and week 3, 4. Um, and that is a standard format what we use at IRI at that time. Predictor is a GFS ensemble mean rainfall. So we are taking the mean of ensemble members. So we are not counting, we are um, constructing the PDF. And for the training, we use 1989 to 2010, and we validate the forecast of 11 to 18. And then we tested for 3 years from 3 season of monsoons, 2022 to 2024. So before going forward, I'll walk you through those what is extended logistic regression. Basically, the extended logistic regression is basically a regression of probability to direct with models deterministic forecast, and plus this is called uh, um, this uh, this is the linear regression kind of with the probability. And when you for particular probability of non-exceedance from 33 and 66% classes is calculated, and the below normal and the normal probability is calculated between probability of 33 and probability difference between probability of not exceeding 33 and probability of not exceeding 66. So these are three category forecast. This ELR is directly provide three tercile forecast on each grid point. And the quantile regression forest is similar to um, a regression tree, and many regression tree are bootstrapping the data, running, um, making the forest, and then collecting the forecast at each leaf node, and then you have a distribution, and then and but this is also used in a probabilistic sense, that the probability of exceedance a particular quantile. So it's a quantile regression. And the methodology, we have a GFS data. We do the post-processing, pre-processing, like a car calculating the week 1, week 2, week 3, 4 averages, and similar to the observation, and matching the observation and um, model forecast dates and stuff, and then pass through the extended logistic regression and quantile regression forest. And we get the probabilistic forecast, validate, um, and then test our test period for both methods. So the first uh, figure, you can see that this is a rank probability score. It's similar to RMSE for deterministic forecast. Basically, it's a cumulative forecast vector, like a three category, cumulative from smallest 133 to like a full probability of 1, and then to observation if you and then sum over each grid point for all the forecasts. And so, we want to check that if forecast like a QRF is making significantly statistically significantly less error, then we use this Diabol Mariano test, which is basically a sign test, because we use observation in both QRF calculation and RPS in both method, and so and apply any other test to test the significance will be not that straightforward. So this sign test is basically testing the coin, and if coin is fair, then the 50% chance you get head, and 50% time you are getting tail, and then that will follow the binomial distribution. And if one outcome is more likely than others, and if it is statistically significant 95th percentile, then it's shown by dots. So the difference, the first row is showing week 1, second row is week 2, and third row is week 3, 4. First is for first um, column is for QRF, second is ELR, and the third column is the difference between ELR minus QRF. So wherever the red areas where the ELR is making more RPS error, probability as compared to QRF, and the dots are those where the difference is significant, and we can see that QRF show lower RPS than ELR across all the lead times, and it's show that it's making a smaller probabilistic error, and it's well aligned with the more aligned with the observed frequencies. Another is a rank probability skill score, and we have a RPS, and then we calculate the RPS for climatological outcome. And then RPSS is simply 1 minus RPS of your model, and then and comparing it with climatology. And if RPSS is positive, then means your forecast is better than climatological forecast. So as we can see that in first row, um, the ELRs week 1, week 2, and week 4. The first is the magnitude of RPS. ELR is less as compared to QRF, and and the second, like especially the central India, the and the uh, northwest, and on all three lead times. And however, there are some regions where, like in Orissa and that, and then in between those southern peninsula, some regions where the forecast from the QRF calibration is little less as climatology, so the negative value of RPSS. So this is the reliability. The reliability means that how we can take all grid points from we combine all forecast from all the grid points, and we want to see the if model issue the for probability of 70% below, and the observed frequency be match. So this probability reliability diagram tells few things. So this is the area prior skill scores. So if your values of reliability are on the reliability diagram remain in those areas, that means your forecasts are useful for decision making. Second, there is a diagonal line. This is a perfect reliability. As close your forecasts remain to those lines, this means your reliability errors are small and your forecasts are more reliable. And third thing is the resolution. This is you can see this the distribution of your forecast probabilities as wide they are, as long these lines are. That means you are resolving the large range of probabilities. And if we see in this reliability diagram, you can see that most of the time both methods are useful skill. They are useful, remain in positive broad skill score region. And the second thing we note that both are close, but in week 1, QRF is better, show the better close to the perfect line, and similar to week 2 and week 3, 4. And also the resolution of QRF is better compared to the ELR. So overall, the quality of calibration, overall, both methods are generally very reliable, but QRF add value in the forecast. The QRF's forecast are more probabilities are more stronger whenever it's giving the forecast, and when a calibration method gives a stronger probability, then there is a chance that if it is wrong, then it will be wrong by 2 class. So to understand that, whenever the probabilities is issued by after calibrating with the QRF, does it match with the how often it falls in the right category? Um, so we have another score to um, check, which is called ignorance skill score. The ignorance is basically like a logarithmic score, and uh, if we have observed forecast, we take the probability in observed state and add at each grid point, and then we take the log negative of the log and accumulate, and then if it is positive, if it is smaller, smaller is better ignorance. But IGGES ignorance score similar to RPSS. It's basically ignorance from model and ignorance divided by ignorance of climatology one minus. The positive IGGS indicate that your forecast has a provide information more than climatology, and it is um, so you can see that ELR uh, QRF is providing more value in forecast as a more content in forecast as compared to ELR on week 1, week 2, and week 3, 4 lead times. And ELR doesn't have like a very small value near methodology in week 3, 4. But on the side of that, there are some great points where the forecast of uh, QRF calibration are a little overconfident, especially there's the small dots in the uh, southwest of India and then maybe in the near the Rajasthan border to the Pakistan. So and then this is the we did the calibration, and then what it will do when it will go in a real time. So and the first column here is the observed percentile. So we have rank the uh, forecast, rank the rainfall weekly accumulated, and then we compare to that climatological ranking to this particular week, and they assign if they fall in above normal, which is blue, and below normal range 30 between 33 and 66 percentile is like a gray shading, and then if it is fall in between um, um, 0 and 33 lower tertile, then it's red, and first is the observed percentile. Similarly, we calculate the raw forecast percentile. So we then models forecast compared with their own climatological ranking, and then we can see that third is the ELR forecast, like a week 1, week 2, and week 3, 4, and fourth is QRF. And you can, this is the case study from 3rd June initialization in 2023. We can see that in week 1, and you can see most of India observed a below normal rainfall. And if we do not do anything to the forecast, just calculate the raw percentile, you can see that the model did a very good job. And this means that the model has skill in week 1 to do that from the initial conditions. And if the ELR forecast does not able to assign any probability in week 1, that was our problem. That was our motivation. Sometimes it just gives you the blank map and doesn't assign any meaningful probability to any grid. And with the QRF, you can see that pattern is matching. And though we are constructing the PDFs, when we compare the constructed PDF, it's very sometimes it's not assigned the values to normal, and that is kind of drawback of as compared to counting. So so in week 1 model is able to assign probability and forecast are more confident as compared to even the raw model forecast, and on in the right areas, and and wherever the model issue the normal category, the uh, the the QRF or any other calibration method will issue like a white area or maybe slightly above uh, or slightly below. But this in the week two also, you can see that model is forecast is concentrated only on the central east side, and the large area of the central and eastern India was below normal, and the forecast able to assign more grade 2 below normal on that. And the areas where the probability was near normal, models issue this weak probability to above normal of maybe 40-45%. And in the week 3, 4, there was uh, the, the model mix. Signal from the raw model is mixed. Like the regions near normal are showing above normal, and and above normal was showing in near normal. So then the two class, one class difference, and there's not much information provided by ELR. However, QRFs is also not assigning the right amount of probability, and the forecast is not very confident. And the reason for that at that time, MISO, this is a MISO uh, index. We can see that MISO was, when the forecast was initialized, the MISO was in the curve in the unit circle. It was not active, and it's briefly become active and propagate through like a couple of phases, and that's why there was no skill on beyond week two. So that is like your dynamical models. Skill comes from dynamical model. The calibration methods has to do calibration only, and that is second case study is from 30 July initialization. That time in 2022, where the flood happened in Pakistan that time. And we can see that though is a weekly average, we can see that some propagation northward and very well organized miso kind of signature. Though it's a weekly and bi-weekly average, we cannot see that much in propagation. And the model was able to give capture the signal, though is has their own biases, but we can see that it is the signal is expanding northward, and that signal is strong up to 1 month, and that's why when their parent model has a skill, dynamical model had some skill, and ELR or any dynamic calibration method will calibrate those forecasts, the signal well, and then you can see that um, uh, showing the probability in above normal rainfall probability in right areas. And even model is able to capture this uh, enhance this below normal probability in this northeastern regions, especially the Nepal border over near the Bihar and UP, below normal rainfall, and also in the southern peninsula below normal. So and the reason for that one, that time that miso was active, is propagated at least 5 phases at the time. So QRF method is similar to the ELR, and both are well calibrated forecast. But issue is with the ELR, that the probabilities are too diplomatic. They are most of the time 45-40, that kind of probabilities are issued. And then QRF improve upon that, and that's by lowering the RPS or RPSS, improving the forecast resolutions. And QRF provide a sharper forecast and informative probability that can be useful for decision making. And one note, if your dynamical model doesn't have skill, the calibration cannot do anything. Calibration is just to create probabilities useful. However, calibration can destroy your model signal if it is not done well, carefully. And that's all from me today. And thank you for listening. And I'm ready for any question and feedback. Hello?
Huh? Okay. So, Bohar, thank you very much for a nice presentation on using quantile forecasting. And I hope you can mention you must have published a paper on this. I think you can share it with all of us. Thank you.
Uh, this paper is submitted and under review, and whenever it's available, I will happy to share.